Okay, we're going to work on the division now of rational numbers. So just a reminder that when we see 10 divided by 2, there's a couple different ways that you can look at that. But the way we're going to see it is how many groups of 2 are there in 10. So there's 1 group, 2 group, 3 group, 4 group, 5 groups of 2. And we can check that because we know that 5 times 2 equals 10. So now if we want to think about 3 divided by a half, we could think about that as how many halves are there in 3. So if I actually make 3, I want to count out how many halves there are to make the 3. So you can see the halves. There's going to be 1 half, 2 halves, 3 halves, 4 halves, 5, 6 halves. So 3 divided by 1 half is actually 6. And so we can check that by saying how much is 6 halves, which is what we were just working on. And so you can see the picture kind of the reverse way, that 6 halves is going to equal 3 wholes. So the answer to 3 divided by 6, just one more time, is going to be 6. So this was just our check. So we're going to keep asking the question in terms of how many are there of something. So like 2 divided by 1/3 is asking how many 1/3s are there in 2. So if we're going to draw that picture, you could draw rectangles or circles, whatever you want. If I'm looking at these as my 2 wholes though, I want to know how many thirds are in there. So I have to break them up. Maybe rectangles are better here. Break them up into thirds. You can see there's 1, 2, 3, 4, 5, 6. So 2 divided by 1/3 is equal to 6. And my check, I guess, before I boxed it, is that 6 of the 1/3 equals 2, which it does. It equals 2 wholes. How about 3/4 divided by 1/8? What does that mean? That one looks a little bit different. It says how many 1/8, so that's still the same, are there in 3/4? But this time we can only draw the 3/4. So let me see. Let me make this one. I'm going to switch back to rectangles. So if I'm looking at 3/4, so there's 1/4, 2/4, 3/4. I want to know how many 8ths are in there. Well, if I have 4ths and I want to turn those into 8ths, that means I really just have to split each of those in half. So I'm going to split those in half. And so I have 8ths now. And so how many 8ths do I have? Well, I have 1, 2, 3, 4, 5, 6. So it looks like 3/4 divided by 1/8 is equal to 6. So the check is that if I have 6/8, which you can see on the picture, 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, that would be equal to 3/4 of the whole, which it is. I can also, without doing it picture-wise, looking at the 6 times 1/8, we've already seen that that's multiplication across. That's 6 over 8, and they both have a 2 in it, so that would become 3/4. So you can kind of see a check again with the definition of multiplication. All right. So for each of the examples, you should be kind of pausing, try it on your own. But for sure, you should pause right now and try this one if you haven't yet. All right, so we want to know 2/5 of 1/10. So how many 1/10ths are in 2/5? So I'm going to draw 2/5. So 1/5 and 2/5. And I want to know how many tenths are in there. So again, tenths I could find, and I kind of made these on purpose nicely to draw, is taking each of my fifths and cutting those in half. And so we can see that there's 1, 2, 3, 4. So the question 2/5 divided by 1/10, the answer to that is going to be a 4. And I can check that by looking at how much 4 times 1/10 will be. I could use the definition and say that's 4/10, but then that reduces to 2/5, which is my check. So the definition for division says that if you're going to take AB divided by CD, the only way we'll equal this EF is if EF is the unique number that when you multiply it by CD, you get AB. So we're just kind of like doing it by checking our multiplication. Now I do want to point out, and it's going to be further ahead too, but we'll see it here as well. If we were trying to figure out what is EF, what is the answer to that division problem, I could treat this like the equations we were looking at and say, okay, well, if I want to solve for X, I need to multiply by the reciprocal. And so we can see that that will equal 1 because they're multiplicative inverses. And so we're really saying that X, which was my EF, is equal to A over B times, it just turned into a multiplication problem, C over D. So just something we'll see on the next page, but this is one way to look at it. And if I look up above, just to see if that is kind of working out to be true, if you look at the first division, or the last division problem we just looked at, if we rewrite this as 2/5 times 10 over 1, you're going to see this is 20 over 5, which is 4. It checks. Let's try one more, just in case you don't believe it. We have 3/4 times 8 over 1. That's 24 over 4, which is 6. Alrighty. So now one common thing before we get on to exploring that a little bit more, there's a big difference between taking half of a number versus dividing by half. And a lot of people use those words interchangeably, but they really mean something different. So I have them both written out here. I'm looking at the first thing saying, find half of 8. So some of us in our head, if I say you have $8, I want you to get rid of half of that. You could say that would be 4. If you want to see a picture of that, I mean, that's taking 8 things, 4, 5, 6, 7, 8, and they're all the same. And I only want half of that. I could take it by halves individually, or I could take half visually of that would be the 4 big holes you see, but I could also say there's a hole, there's a hole, there's a hole, there's a hole, so we could get 4. So I feel like we're okay with that. But then a lot of people say, oh, well, that's just the same as 8 divided by a half. But that's not what it is. 8 divided by 1/2 is asking me how many halves are in 8. Well, if you just kind of think about that a little bit, 8. Well, 8 holes, how many halves are in there? Each 8 is made up of 2 halves. And so that's going to be 16. The picture of that, right, we could kind of see it over here, but I'll redraw it. Let's make 8 and cut them in half. And so you can see all of those halves. We have 1 half, 2 half, 3 half, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 halves. Big difference in those answers. So just something to keep in mind. All right, we're going to look at that algorithm, which goes through with what I said, that if you have these two fractions, A, B, and C, D, and you're going to divide them, we can actually rewrite that as a, oops, I kind of fix my notation here. This should have been a B, sorry about that. So that's going to still be A over B times, this is the change, it will be now D over C. So it's multiplied by the reciprocal. So we saw one reason why that happened because of the multiplicative inverse. But another reason why this works, and often this is the way that's shared with elementary school students because they have to know why this algorithm works, is they could take something like 2 over 3 divided by 5/7 and actually rewrite it as a big fraction like 2 over 3 over 5 over 7. And then they know that you can multiply any fraction by 1. And so we're just going to write that as a very special one. So we're going to have the 2/3. Oopsie, let me fix that. We're going to have the 2/3 over 5/7. And the fancy one that we're going to use is 7 over 5, 7 over 5. And the reason why we're going to be doing that, you can see that right here. 5/7 times 7/5 we already know is 1. And so we're going to get 2/3 times the 7/5. And you can see that when you divide by that 1, this is just 2/3 times 7/5. So what we're showing is that division of two fractions is really just multiplication where you flip over the second fraction. So it's not about memorizing, it's really understanding how all these operations and properties work together. All right, so let's see, we have a little example of a word problem relevant to today, I think. A person has 29.5 yards of material to make face masks. Each face mask requires a 1/4 yard of material. And so we're asking how many face masks can be made. So really it's saying I have 29.5 yards that I need to divide up, and it's going into little sets of 1/4. So another way I could ask the question is how many 1/4 are in 29.5. And so if we rewrite it using this algorithm, I would like to write 29.5 as a single fraction because the algorithm shows a single fraction. And so that will be 59/2. So 2 times 29 is 58, plus the 1 is 59/2. And I'm going to say times 4/1. Well, 59 times 4/2 will end up being 118. So we can make 118 face masks. Now, just to see how this still fits with the picture, it's saying how many 1/4 are in 29.5. Like if you actually drew, let's see, 4, 5, 6, 7, 8, 9, 10. I'm going to draw this really fast. So I have 20 right here, and then I'm going to have 29. So there's 29. If you think about it, each whole has 4 pieces. Well, that means what we're saying is that there are 4 1/4 in a whole. And then we also have that little half guy, right? Because it's 29.5. So right now I have 29 times 4. That's how many fourths that I have. So that 29 times the 4 is equal to the 116. But then I also have the half. So if I have just the half, I want to know how many 1/4 are in there. Well, that's breaking that again in half. So I have 2/4 in there. So I'm going to have 116 plus those 2. I'm going to have 118 fourths, which tells me I have 118 masks. And will there be any material over? Nope. We used it all up. All right. So the last thing we're going to look at is reviewing some of the properties of exponents. And one of the things that we want to see is a certain pattern. So let's see, 2 to the 4th, we already know what that is. That's 2 times 2 times 2 times 2, which will be 16. 2 to the 3rd is 2 times 2 times 2, which equals 8. 2 squared is 4. And so you can look each time it's dividing out a 2. It's 1 less 2. And you could kind of see I left a space on purpose, so you kind of see all those 2's kind of being divided out. So then if I continue on, 2 to the 1, that'll just be a 2, which is 2. And so then I have 2 to the 0. So if I divide out by another 2, well, that's just going to be left with 1. And you can see that with this pattern here, dividing by 2, we get 1. So then what does 2 to the -1 mean? Well, that means I'm going to divide by 2 again. 1/2 divided by 2 will put me at 1/2. 2 to the -2, and that's dividing by a 2 a second time, which is really putting 2 2's on the bottom. Or 2 squared, we write that as 1/4. And so looking at our numbers here, we have 2 to the -2 is 1/4. But let's look at this row. 2 to the 2nd power is 4. Then we could look at 2 to the -1. This guy was 1/2. Let's compare it to this guy. 2 to the 1 is 2. So what's happening with these negative exponents? If you think you know, then you should be able to figure out what 2 to the -4 will be. Yep, it's 1 over, you're dividing by 2 4 times now, so that's 2 times 2 times 2 times 2, but that will be 1/16. this should be the reciprocal of 2 to the 4th. Positive 2 to the 4th. So when we flip over to the next page, I'm going to rewrite some of these properties will look really familiar, and then there's going to be a couple more for working with exponents. And they're not necessarily something you memorize, but to see different patterns and other relationships. So the first one that I'm going to write is what we saw on the previous page, that if you have anything to the 0 power, that will become a 1 because it just divides out everything perfectly. If you have a negative exponent, it just means reciprocal. So I'm going to write 1 over a to the m. And a reminder for an example that if you have like 2 to the negative 3, that was 1 over 2 to the 3rd. And then again, a few more familiar ones, a to the m times a to the n. This just means I have ma's and then I have another na's. So I have a lot of a's altogether, a total of m plus na's multiplied. If I have a to the m over a to the n, that means I have ma's over na's. So these guys will cancel out some of those guys. So I'm going to have a to the m minus n. Again, if you need a little example of each of these, I have like 2 to the 3rd times 2 squared. This will be 2, 2, 2, and then another 2, 2, so it's 2 to the 5th altogether. Or if I have like 2 to the 3rd divided by 2 to the 2nd, that'll be 2, 2, 2, 2 over 2, 2. Cancel or reduce, and we're left with a single 2 or 2 to the 1. Then we also have seen before if you have like a to the m to the n power, and for that it will be a m n. You multiply those guys. So again, examples are kind of nice. If I have 2 to the 3rd to the 2nd power, that'll become 2 to the 6th. But the reason I know that is because 2 to the 3rd to the 2nd means 2 to the 3rd and then another 2 to the 3rd. But that would be 2 3 times, and then another set of them 3 times. So that's altogether 2 to the 6th. All right, now the ones more related to these rational numbers. If you have a fraction, a rational number to the mth power, because of the way the fractions have been multiplying, that just means you're going to have a m times m b m times. And just a little note that b can't be 0. Then if we have a over b, like a whole fraction to that negative exponent, it's going to be the reciprocal of that guy, and it will have a positive power now because of the meaning of that negative exponent. And I guess we already have seen this one too. This one isn't a fraction, but it says if you have a product to a power, it's going to be each guy to a power, which should make sense also using the commutative property. So we're going to use those to simplify a few things down below here. And so for part 1, there's a couple different ways that you could do number 1. Right away, I'm thinking that I have this negative 3, so that's going to put me in the denominator. So I already have an a, then I'll have an a to the 3rd. But together, that would be 1 over a to the 4th. If you like the exponent rules, it said if you have the same base, you could subtract. So that would be a to the negative 3. There's really like a 1 on the bottom a. So we're going to say minus that 1. That's a to the negative 4, but that would still be 1 over a to the 4th. For part 2, we have a to the negative 4 cubed, but cube means we're going to have a to the negative 4 3 times, so that would become a to the negative 12. And I have a to the negative 4 still on the bottom. I can use my exponent rule that says I could subtract the exponents, or I could do one other thing. So I'm going to minus that negative 4. So this will be a to the, if you're going to take off 4 negatives, that means you're only going to have 8 negatives left, but that would be 1 over a to the 8th, make that positive. But the other way that I was thinking is that you could use the definition of the negative exponents and like flip each of those. So a to the 4th would be on the top and a to the 12th would be on the bottom. And then you could say a to the 4 minus 12, but that's still a to the negative 8. So 1 over a to the 8th. So either way is fine. I'm just showing you both ways. It depends on how you think through things. For number 3, we're taking 1/2 divided by, well, 1/2 again, but this has 10 of them divided by 2 of them. So I kind of want to rewrite this 1/2 to the 10 over 1/2 to the second. Those are the same bases. So the exponent rule says I could take 1/2 to the 10 minus 2. That's 1/2 to the 8th power. But you could simplify that, but we could leave it like that. Or you could actually take it as like 1 to the 8th over 2 to the 8th, if you like that better. 1 over 2 to the 8th. Both of those would be fine. For part 4, I noticed that 3/5 and 5/3, it's almost the same as the last problem, like if I try and rewrite it. But 5/3 is the reciprocal. So what I could do is say, well, this could really be rewritten as 3 over 5 to the -4 power. So now if I have that, I can bring this to the top. So that would look like 3 over 5 to the 7th power times still 3 over 5, but now to the +4. When it moves, it changes to that positive sign. So then altogether, I have 3/5, well, 11 of them, which would be my final answer. You don't have to put that into a calculator. All right, last couple questions here, just estimating. We're using some mental math similar to our whole number strategies. When I look at number 1, I see 11/12. That is so close to 1. So I see this as 3 plus 1. So really 4 times that 8. So that's what it's really close to, which would be 32. When I look at question 2, I notice it says 3/2 divided by 1/2. So really it's like how many halves in 3.5? Well, I already know that in the number 3, there's 6 halves, and then there's another half sitting right there. So it looks like that would be about 7. And actually that is equal to 7. So that's more about a mental math on that one. And then for number 3, it says 4.5 divided by 2. So how many 2's in 4.5? That doesn't really make too much sense, except that 4.5, I guess I could say that that's close to 4. Divide that by 2, so that's 2. So it's close to 2 is what I'd say. All right, that's it. Division.